In this last video for section 13.2, we're just going to do a few more examples of substitution. Okay, so let's consider an example. Okay, so we're trying to find the antiderivative of e to the negative 3x, where x is considered to be the variable. So remember, hopefully you have those hints written down that I showed you in the last two videos. And one place that is good to look for a choice for a u substitution is up in the exponent of e, right? Notice that if this was plain old e to the x, we would already know what the antiderivative of it is, right? But it's not plain old x up here, so perhaps that we can consider to be our trouble spot here, right? Okay. And locating our trouble spot allows us to have that be a candidate choice for u. So let's go ahead and try that. So let's let u equal negative 3x. Okay. When we do that, then notice that we get what du dx is what? What's the derivative of negative 3x? It's negative 3. Okay, so one thing that I didn't mention in the last videos is that usually so far when I've gone through these problems and I've gotten to this step, I usually move the dx up, right? I usually say du is equal to negative 3 dx, right? And then I try sort of noticing if I have what is here, this negative 3x dx, and just replacing du. What some people prefer to do is always to do the following. They prefer to just isolate the dx and plug that in, right? In this one, it's not going to make too much of a difference, but you'll see what I mean for the next coming examples, right? So what I mean by that is some people prefer to always just write what dx equals and then put that expression here for dx, and then hopefully other stuff cancels, right? So for in this case, it would be du over negative 3 is dx. Right. Okay, so when I now start rewriting this integral here, I get what? This is e to the negative 3x is u, so this is e to the u, and dx is du over negative 3. Okay, remember that this negative 3 living down here, this could be rewritten as times what? Negative 1/3 du, right? Okay, because du over negative 3 is the same thing as negative 1/3 du. Those are the same two things. But this sort of emphasizes that this fraction can be brought out front of this integral as a negative 1/3, right? And this is then integral e to the u du. Okay. The negative 1/3 is just a constant living out front that we don't really have to do anything with besides rewrite it, right? Okay. The antiderivative of here e to the u, and where u is the variable, antiderivative is e to the u. And then we add a constant of integration. Again, remember not to be finished at this point, but remember that you have to rewrite it with the original variable being used, and the original variable was x, so replace that u with negative 3x. So negative 1/3 e to the negative 3x plus c. And now that one is complete. Again, pause the video, check to see that this antiderivative is correct by taking its derivative and getting the integrand in here, e to the negative 3x. Okay, let's try another example. Okay, in this one we've got 5t squared t to the third plus 4 all raised to the negative second power, and the variable is t. I think all of our previous ones have had x as the variable, but again, we can use whatever variable we want, right? It doesn't really matter. So one suggestion of where I've told you to look for a good choice for u, remember, is inside of parentheses, right? And notice in here, this is something yucky being raised to a negative 2 power, okay? So again, if it's the wrong choice, we'll just erase and try again, but let's choose the stuff inside the parentheses as our u, okay? So let's let u equal t to the third plus 4. Okay, and then remember we have to sort of figure out how to replace that dt, sometimes dx, right, but dt with du. So du dt is the derivative of our choice of u here, which is 3t squared. Okay, and this is the point at which, remember I told you that you have an option, right? Okay, so I usually move the dt up, so this is du equals 3t squared dt. And in some of our previous examples, it's been really easy for us because this expression has like automatically been found in our integral up here, right? In this case, it's not true, right, that we don't automatically have this expression here. So, what some people like to do is just simply solve for this dt or dx thing, like I was saying over here a second ago. They just solve for dt in this expression, and then they allow some sort of canceling to happen, and you'll see what I mean in just a second, right? So let's just solve for dt here. So du over 3t squared is dt. And in my experience, lots of people seem to like this better, maybe because it's always the same thing. You always just solve for dt or dx, whichever one you have right here. You solve for that in your choice of substitution down here, right? You just solve for it here, and you just replace this expression up here and allow all the rest of it to sort of fall together. Okay, so let's see how that would work. When I start rewriting now, okay, I'm going to rewrite this integral. Okay, if you're going to choose this way of just rewriting dt as this stuff over here, then that means all this in the front is just going to hang out here, because right, 5t squared is not anything in terms of u here, right? U is the stuff inside. But let's see what happens. 5t squared is in the front. The stuff inside of the parentheses, that's u. And I know you're already nervous, right? You're already nervous because you're saying, there's t's that haven't been replaced in terms of u's, right? Give it a second. Let's see what happens. What is dt? dt is du over 3t squared. Okay? And this is what I mean by people usually prefer this, right? Because if you just solve for dt or dx, whichever one you have at the very beginning of the problem, and just replace it there, usually what ends up happening is some cancellation, because notice here that the t squared and the t squared here cancel, right? Okay, so you didn't have to think about trying to write exactly what you had, right? Because we had a 5t squared dt. We didn't have 5t squared dt. We only had 3, so that gets a little bit messy, right? So we don't even have to try to think about how to replace that. We can just say replace the dt with what its equivalent expression is here, and then allow things to cancel as necessary, okay? So now that we've got things canceled, let's go ahead and rewrite what we have left. So this is the integral of what? We've got 5u to the negative 2 du over 3. Okay, well, there's a bunch of constants here. The 5 is a constant, the 3 is in the denominator as a constant, but that means we could pull a 5/3 out, right? 5 in the top, 3 in the bottom, comes out as a 5/3 integral u to the negative 2 du. Okay, and now we can do the antiderivative of this thing. So this is 5/3. What's the antiderivative of u to the negative 2? Well, that's a power. We have to reverse the power rule, right? Okay, so let's add 1 to this power. Negative 2 plus 1 is negative 1, divided by a new power of negative 1, and we add our constant of integration. Okay, we're not done. We got to replace that u with our choice of u up at the top. And that negative 1 can go up front with the constant, so I have negative 5/3. And then we can write, what is u again? It's t to the third plus 4, all that raised to the negative 1, plus c, okay? And now, seriously, is a time when you should pause the video, and you should check to be sure that this function we have right here, right? You need to check to be sure, because this is our possible final answer. Take this thing right here, take its derivative, and be sure that you get this integrand, right? You should get that as an answer. And if you don't, we did something wrong, right? Okay, but you will, okay, and it'll look great. Okay, so let's see. I think we have enough time to do one more example. And this one's a little bit different, okay? Requires us to do something a little bit sneaky. Okay, but let's try it. Okay, so we're doing the antiderivative of x square root of x plus 1. Okay, and remember, one of my suggestions for you of where to possibly choose your u is inside of a radical, right? Okay, so let's give that a shot and see what happens. So let's let u equal the stuff inside the radical. Okay, if u is the stuff inside the radical, then du is equal, let's see, du dx, I should say. Du dx is the derivative of this stuff, which is just 1, which means that what? Du equals dx, right? So let's see if I scoot that over a little bit. So this equals 1. So that means that du equals dx. Okay, so let's start rewriting our integral now. So if I rewrite this as integral. Again, I'm going to let that x just try to cancel away, okay? So, because I'm just going to replace the dx. Square root of x plus 1 is u. Dx is du. Hold on a second. The x isn't going to cancel. Oh boy. That's not good, because usually here, like in the previous example with this du, usually when I replace that, this x like gets taken away, right? Somehow it cancels or something, right? Well, it's not going to cancel. So that's not good. So what should we do? Well, maybe we should remember that our goal here is to not just replace all the parts that we labeled, right? We called this as u, we called this dx as du. But remember that our entire goal with substitution is to replace everything with stuff in terms of u or du, right? So what that means is that we need to replace that x right there with something in terms of u. Like, do we know what x is in terms of u? Like, do we know x equals blah, 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 something in terms of u? I'm not sure. Well, if you're not sure, maybe you could look to see, do you have a way that u and x are related to each other? Well, that's true. We do. We have this right here, right? We have u is x plus 1. Well, wait a minute. If u is x plus 1, doesn't that mean that x is equal to, wait a minute, if x, let's see, if x is equal to u minus 1. Aha! Yes, because that's how they're related, right? U is x plus 1, so x is u minus 1, right? Subtract the 1 over. Aha! Great. So that means then that we actually could have completely rewritten this instead as, let's see, let's just erase some stuff. And we'll write in black. Okay, so that means that this x right here is actually u minus 1, right? But notice it says x times a square root, and x is all of u minus 1. So that means I need to say this times the square root, right? Because this says x times the square root, right? So make sure you're using parentheses. And the stuff inside is just u, and dx is du. Aha! Everything is in terms of u. Great. Okay. And you're probably saying to yourself, why did we even bother doing that? This looks no better than what we started with. Well, it actually is better, because notice that before, this x couldn't interact with the stuff inside the radical, right? Because you can't take an x across the radical like this. But you can actually take this radical across this subtraction, right? And so here we can write this as, let's see, if I use the distributive property, this is u square root of u minus the square root of u du, right? If I just distribute here, and that means that if I use a different color, that means that this square root is going to here as well as here, right? Good. Well, how do these interact here? How do those u's interact? What's u times the square root of u? Well, don't forget that u times the square root of u is the same as u times what, u to the 1/2, right? So this is integral of u to the 3/2, okay, because it's u times u to the 1/2 minus, and this is just u to the 1/2 du. Again, that's a property of exponents, right? Is that u times u to the 1/2. We add the powers, so that is u to the 3/2, because that's to the first power. Okay, and now we can do antiderivatives, because these are just powers of u. So this is u to the, let's see, 3/2 plus 1 is 5/2 over 5/2 minus u to the, add 1, that's 3/2 over 3/2 plus c. Okay, and we can finish up this problem by replacing those u's with our choice for x, right, in terms of x plus 1, right? And of course, if you want to flip the fractions, that's fine. So we would go 2/5 times x plus 1 to the 5/2 minus 2/3 x plus 1 to the 3/2 plus c. And that's our final answer right there. Again, check this thing, take its derivative, make sure you get this thing inside of here. You might have to do, if you do check this, you might have to do a little bit of algebra to be able to see that these two things are the same. But this trick here, where we actually had to do this step in blue, where we had to like be a little sneaky here, this part right here. Okay. Whenever you have to do that, where you have to sort of use your choice of u and then be sneaky to like say what else it equals to use it somewhere else in the integrand, right? When I do that, that's actually using the technique of what is called back substitution.